In the mathematical field of differential geometry, a metric tensor is a type of function which takes as input a pair of tangent vectors v and w at a point of a surface and produces a real number, scalar g, in a way that generalizes many of the familiar properties of the dot products of vectors in Euclidean space. In the same way as a dot product, metric tensors are used to define the length of an angle between tangent vectors. A metric tensor is called positive definite if it assigns a positive value to every non-zero vector. A manifold equipped with a positive definite metric tensor is known as a Riemannian manifold. Through integration, the metric tensor allows one to define and compute the length of curves on the manifold. On a Riemannian manifold, the curve connecting two points that has the smallest length is called the geodesic, and its length is the distance that a passenger in the manifold needs to traverse to go from one point to the other. Equipped with this notion of length, a Riemannian manifold is a metric space, meaning that it has a distance function d whose value at a pair of points p and q is the distance from p to q. Conversely, the metric tensor itself is the derivative of the distance function. Thus the metric tensor gives the infinitesimal distance on the manifold. While the notion of a metric tensor was known in some sense to mathematicians such as Carl Gauss from the early 19th century, it was not until the early 20th century that its properties as a tensor were understood by, in particular, Gregorio Ricci-Curbastro and Tullio Levi-Civita, who first codified the notion of a tensor. The metric tensor is an example of a tensor field. The components of a metric tensor in a coordinate basis take on the form of a symmetric matrix whose entries transform covariantly under changes to the coordinate system. Thus a metric tensor is a covariant symmetric tensor. From the coordinate-independent point of view, a metric tensor is defined to be a non-degenerate symmetric bilinear form on each tangent space that varies smoothly from point to point. Introduction. Carl Friedrich Gauss in his 1827 Disquisitiones Generalis circa superficies curvae considered a surface parametrically, with the Cartesian coordinates x, y, and z of points on the surface depending on two auxiliary variables u and v. One of the chief aims of Gauss' investigations was to deduce those features of the surface which could be described by a function which would remain unchanged if the surface underwent a transformation in space, or a change in the particular parametric form of the same geometrical surface. One natural such invariant quantity is the length of a curve drawn along the surface. Another is the angle between a pair of curves drawn along the surface and meeting at a common point. A third such quantity is the area of a piece of the surface. The study of these invariants of a surface led Gauss to introduce the predecessor of the modern notion of the metric tensor, arc length. If the variables u and v are taken to depend on a third variable, t, taking values in an interval a, b, then we'll trace out a parametric curve in parametric surface M. The arc length of that curve is given by the integral where represents the Euclidean norm. Here the chain rule has been applied, and the subscripts denote partial derivatives. The integrand is the restriction to the curve of the square root of the differential where the quantity ds in is called the line element, while ds2 is called the first fundamental form of M. Intuitively, it represents the principal part of the square of the displacement undergone by when u is increased by d units, and v is increased by dv units. Using matrix notation, the first fundamental form becomes coordinate transformations. Suppose now that a different parameterization is selected, by allowing u and v to depend on another pair of variables u and v. Then the analog of for the new variables is the chain rule relates E, F, and G to E, F, and G via the matrix equation where the superscript T denotes the matrix transpose. The matrix with the coefficients E, F, and G arranged in this way therefore transforms by the Jacobian matrix of the coordinate change. A matrix which transforms in this way is one kind of what is called a tensor. The matrix with the transformation law is known as the metric tensor of the surface. Invariants of arc length under coordinate transformations. Ricci-Curbastro and Levi-Civita first observed the significance of a system of coefficients E, F, and G that transformed in this way on passing from one system of coordinates to another. The upshot is that the first fundamental form is invariant under changes in the coordinate system, and that this follows exclusively from the transformation properties of E, F, and G. Indeed, by the chain rule, so that length and angle. Another interpretation of the metric tensor, also considered by Gauss, is that it provides a way in which to compute the length of tangent vectors to the surface, as well as the angle between two tangent vectors. In contemporary terms, the metric tensor allows one to compute the dot products of tangent vectors in a manner independent of the parametric description of the surface. Any tangent vector at a point of the parametric surface M can be written in the form for suitable real numbers p1 and p2. If two tangent vectors are given, then using the bilinearity of the dot product, this is plainly a function of the four variables a1, b1, a2, and b2. It is more profitably viewed, however, as a function that takes a pair of arguments or equals a1, a2, and b equals b1, b2, which are vectors in the UV plane. That is, put this as a symmetric function in A and B, meaning that it is also bilinear, meaning that it is linear in each variable A and B separately. That is, for any vectors A, B, and B in the UV plane, and any real numbers mu and lambda. In particular, the length of a tangent vector A is given by and the angle theta between two vectors A and B is calculated by area. The surface area is another numerical quantity which should depend only on the surface itself, and not on how it is parameterized. If the surface M is parameterized by the function over the domain D in the UV plane, then the surface area of M is given by the integral, where times denotes the cross product, and the absolute value denotes the length of a vector in Euclidean space. By Lagrange's identity for the cross product, the integral can be written where det is the determinant. Definition: let M be a smooth manifold of dimension n. For instance, a surface or hypersurface in the Cartesian space Rn+1. At each point Pm there is a vector space Tpm, called the tangent space, consisting of all tangent vectors to the manifold at the point P. A metric at P is a function Gp which takes as inputs a pair of tangent vectors xp and yp at P, and produces as an output a real number, so that the following conditions are satisfied. Gp is bilinear. A function of two vector arguments is bilinear if it is linear separately in each argument. Thus, if up, Vp, Yp are three tangent vectors at P and A and B are real numbers, then Gp is symmetric. A function of two vector arguments is symmetric provided that for all vectors xp and yp, Gp is non-degenerate. A bilinear function is non-degenerate provided that, for every tangent vector xp0, the function, obtained by holding xp constant and allowing yp to vary, is not identically zero. That is, for every xp0 there exists a yp such that gp0. A metric tensor G on M assigns to each point P of M a metric Gp in the tangent space at P in a way that varies smoothly with P. More precisely, given any open subset U of manifold M and any vector fields X and Y on U, the real function is a smooth function of P. Components of the metric. The components of the metric in any basis are vector fields, or frame. F equals are given by the n2 functions Gij, F, form the entries of an n times n symmetric matrix, Gf. If for two vectors at Pu, then the value of the metric applied to V and W is determined by the coefficients by bilinearity, denoting the matrix by G, F, and arranging the components of the vectors V and W into column vectors V, F, and W, F, where V, F, T and W, F F, T denote the transpose of the vectors v, f, and w, f, respectively. Under a change of basis of the form for some invertible n times n matrix A equals, the matrix of components of the metric changes by A as well, that is, or, in terms of the entries of this matrix. For this reason, the system of quantities Gij, f, is said to transform covariantly with respect to changes in the frame f. Metric in coordinates a system of n real-valued functions, giving a local coordinate system on an open set U in M, determines a basis of vector fields on U. The metric G has components relative to this frame given by relative to a new system of local coordinates. Say the metric tensor will determine a different matrix of coefficients. This new system of functions is related to the original Gij by means of the chain rule, so that, or, in terms of the matrices G, F equals and G, F equals, where dy denotes the Jacobian matrix of the coordinate change. Signature of a metric associated to any metric tensor is the quadratic form defined in each tangent space by if Qm is positive for all non-zero xm. Then the metric is positive definite at M. If the metric is positive definite at every mm, then G is called a Riemannian metric. More generally, if the quadratic forms Qm have constant signature independent of M, then the signature of G is this signature, and G is called a pseudo-Riemannian metric. If M is connected, then the signature of Qm does not depend on M. By Sylvester's law of inertia, a basis of tangent vectors she can be chosen locally so that the quadratic form diagonalizes in the following manner for some p between 1 and n. Any two such expressions of Q will have the same number p of positive signs. The signature of G is the pair of integers, signifying that there are p positive signs and n minus p negative signs in any such expression. Equivalently, the metric has signature if the matrix Gij of the metric has p positive and n minus p negative eigenvalues. Certain metric signatures which arise frequently in applications are: if G has signature, then G is a Riemannian metric, and M is called a Riemannian manifold. Otherwise, G is a pseudo-Riemannian metric, and M is called a pseudo-Riemannian manifold. If M is four-dimensional with signature or, then the metric is called Lorentzian. More generally, a metric tensor in dimension n other than 4 of signature is sometimes also called Lorentzian. If M is 2n-dimensional and G has signature, then the metric is called ultra-hyperbolic. Inverse metric let F equals be a basis of vector fields, and as above let G, F be the matrix of coefficients. One can consider the inverse matrix G, F, minus 1, which is identified with the inverse metric. The inverse metric satisfies a transformation law when the frame F is changed by a matrix A via the inverse metric transforms contravariantly, or with respect to the inverse of the change of basis matrix A, whereas the metric itself provides a way to measure the length of vector fields. The inverse metric supplies a means of measuring the length of covector fields, that is, fields of linear functionals. To see this, suppose that alpha is a covector field, to wit, for each point P. Alpha determines a function alpha p defined on tangent vectors at P so that the following linearity condition holds for all tangent vectors xp and yp, and all real numbers r and b. As p varies, alpha is assumed to be a smooth function in the sense that is a smooth function of P for any smooth vector field X. Any covector field alpha has components in the basis of vector fields F. These are determined by denote the row vector of these components by under a change of F by a matrix A, alpha, F, changes by the rule that is, the row vector of components alpha, F, transforms as a covariant vector. For a pair alpha and beta of covector fields, define the inverse metric applied to these two covectors by the resulting definition. Although it involves the choice of basis f, does not actually depend on f in an essential way. Indeed, changing basis to fa gives so that the right-hand side of equation is unaffected by changing the basis f to any other basis fa whatsoever. Consequently, the equation may be assigned a meaning independently of the choice of basis. The entries of the matrix G, F, are denoted by Gij, where the indices I and j have been raised to indicate the transformation law. Raising and lowering indices in a basis of vector fields F equals any smooth tangent vector field X can be written in the form for some uniquely determined smooth functions v1, vn. Upon changing the basis f by a non-singular matrix A, the coefficients vi change in such a way that equation remains true. That is, consequently, v fa equals a minus 1 v f. In other words, the components of a vector transform contravariantly under a change of basis by the non-singular matrix A. The contravariance of the components of V, F, is notationally designated by placing the indices of I, F, in the upper position. A frame also allows covectors to be expressed in terms of their components. For the basis of vector fields F equals, define the dual basis to be the linear functionals such that is, theta I, F, equals delta G, the Kronecker delta. Let under a change of basis FFA for a non-singular matrix A, theta, F, transforms via any linear functional alpha on tangent vectors can be expanded in terms of the dual basis theta where A, F, denotes the row vector, A1, F. And f. The components I transform when the basis f is replaced by fa in such a way that equation continues to hold. That is, whence, because theta fa equals a minus 1 theta f, it follows that a fa equals a f a. That is, the components are transformed covariantly. The covariance of the components of A, F, is notationally designated by placing the indices of I, F, in the lower position. Now, the metric tensor gives a means to identify vectors and covectors as follows. Holding xp fixed, the function of tangent vector yp defines a linear functional on the tangent space at P. This operation takes the vector xp at a point P and produces a covector gp. In a basis of vector fields F, if a vector field X has components V, F, then the components of the covector field G in the dual basis are given by the entries of the row vector under a change of basis FFA. The right-hand side of this equation transforms via so that a fa equals a f a. A transforms covariantly. The operation of associating to the components of a vector field V, F, equals V1, F, V2, F, Vn, F, T. The components of the covector field A, F, equals A1, F, A2, F, and F, where is called lowering the index. To raise the index, one applies the same construction but with the inverse metric instead of the metric. If A, F, equals A1, F, A2, F, and F, are the components of a covector in the dual basis theta, F, then the column vector has components which transform contravariantly. Consequently, the quantity X equals Fe, F, does not depend on the choice of basis F in an essential way, and thus defines a vector field on M. The operation associating to the components of a covector A, F, the components of a vector V, F, given is called raising the index. In components, is induced metric. Let U be an open set in Rn, and let phi be a continuously differentiable function from U into the Euclidean space room, where m greater than n. The mapping phi is called an immersion if its differential is injective at every point of view. The image of phi is called an immerse submanifold. Suppose that phi is an immersion onto the submanifold M-room. The usual Euclidean dot products in room is a metric which, when restricted to vectors tangent to M, gives a means for taking the dot product of these tangent vectors. This is called the induced metric. Suppose that V is a tangent vector at a point of U, say where A are the standard coordinate vectors and Rn. When phi is applied to U, the vector V goes over to the vector tangent to M given by on two such vectors, V and W. The induced metric is defined by it follows from a straightforward calculation that the matrix of the induced metric in the basis of coordinate vector field Z is given by where d phi is the Jacobian matrix.